Welcome to Abstract Synthesis, where we share the stories behind interesting academic papers in the world of program synthesis and symbolic AI. Brought to you by AGI Research Lab and DIA, I'll be your host, Brian Landers. I have a bit of a cold today, so forgive any voice malfunctions, but we should be able to get on with that. I'm really excited for today's guest because he is a part of the team at Microsoft that is legendary in the program synthesis world. This is the PROSE team, P-R-O-S-E, PROSE, led by Sumit Gulwani, see if I'm pronouncing that right later, creator of the famous flash fill feature in Excel. So this is a really cool team and also just cool research. Our guest today has worked in directions like predictive program synthesis, but with the explicit goal of making people more productive and automating repetitive tasks. So very real world application, which is a fun aspect of this kind of AI. This isn't just theoretical stuff. This is being used in some of the biggest products in the world, like, Microsoft Excel. We're going to go deep on his paper, Semantic Programming by Example with Pre-trained Models. And that is neurosymbolic magic, my friends. So we are excited to hear this is exactly what we want to cover on the show. So welcome to the show. Can you please introduce yourself?
Hi, my name is Gust Verbruggen. I am a researcher on the PROSE team. I started after all of the core flash fill stuff had been established quite well, but right at the time when LLMs were popping off. So I joined by actually combining the LLM stuff with the flash fill stuff. That were exciting times. Before that, I did my PhD at KU Leuven. I'm working on program synthesis for data wrangling, but by then there was no LLMs yet. It was all purely symbolic.
Got it. All right. This is super exciting because you brought this sort of new tech to the, more traditional symbolic side of things. And again, for consumer apps, which I think is just so exciting. But all right, PROSE team, we mentioned it. What do you all do? Like, what is it? I know even on the website, mentioning the team, it talks about program synthesis. So you can see why I'd be excited to have you on the show. You're a superstar in this world. But yeah, what do you all get up to specifically on the PROSE team at Microsoft?
So it's been evolving quite a lot. It started off being very like what the name says. PROSE stands for Program Synthesis by Examples. And in the beginning, all of the program synthesis that we were working on was a user giving intent through examples. So the user was not describing what they were doing. They were just doing their task. The synthesizer would pick up the examples of what the user did as some kind of intent and then predict a formula or a program to automate that intent. The most famous example is, of course, flash fill in Excel, where if you are creating a new column and you're manually filling in some values in that column, it will automatically learn a program to fill in the rest of the column for you. Imagine something like taking a first name and a last name column, concatenating them with a dot and adding an @company.com to it. The same kind of like technology also held up very well for repetitive edits in programs. Imagine you have a function defined somewhere, and so you are adding a new argument to it. If the model sees you making this change 2 times, the sequence of steps that you're taking, so the sequence of transformations, the before-after steps, can also be turned into input-output examples. And these input-output examples can then be used to learn a transformation on your program code to actually make this change everywhere throughout your code base. Of course, that's something that's now been changed, taken over mostly by LLMs. But especially for the case of flash fill, I think it's still like extremely valuable to have the symbolic stuff. Then the framework is also very flexible. There were some applications of predictive program synthesis where instead of an example, as soon as you have a very good heuristic on like what the constraints that you want to have, for example, for a table, you know that a column is very likely to be of a consistent data type. Like if you have like one column, there's likely to be like numbers or strings or dates, but not a mixture of them. So if you then give it like a web page or something, it could also learn a small program that extracts the table from these web pages. So all of this was like the core symbolic stuff where the intent was given through like an example or some heuristic or properties of what the example would look like. Then LLMs came and then it kind of like changed because with the advent of LLMs, right? And with like the language aspect in, models, like the deep, large neural networks becoming more important, the way of specifying that intent kind of like changed. Nowadays, maybe not most, but a lot of people aren't writing their code by hand anymore. They are using these coding assistants to actually do their programming for them, right? Because it allows you to very easily say what you want to do in natural language and then just generate a bunch of code that executes your task. And so that's something that many people on the PROSE team are now working on, specifically for example, Excel agent, where the goal is to learn a piece of code that will transform a spreadsheet to do like very complicated tasks, like, create a complete model, like financial model or something. And then it will go ahead and it will not just change the spreadsheet. It will actually write a piece of code that will change the spreadsheet for you.
Very cool.
Yeah.
Makes total sense. It's neat to hear the way you all have started layering in LLMs, but you still see the value in the symbolic side. So, and that's definitely the focus of our show. So I want to make sure we feature that side of things. I think it's a bit underhyped these days. What do you think?
I agree completely, right? It's always very exciting to try and push a new LLM feature into some product, but then it always ends up being more expensive than we planned it to be, right?
Yeah.
So you could very easily ask any language model to do the same task that FlashFill is doing right now, but it will cost you a lot of tokens for a task that FlashFill can solve for free on consumer hardware, right? It runs in milliseconds on a laptop, right? Making it like a very, very powerful approach for something where the specification is something like examples and the task is not too semantic. It's also very, very good, right? I think I'm not sure about like the latest benchmarks for the latest models, but at least last year, language models were only able to get like 80-90% on a lot of the benchmarks that were used for example, the FlashFill++ algorithm, just because these types of constraints, there's kind of like a context switch, right? These types of examples is not something that language models commonly see during their training data. I mean, some people write good unit tests and they write some kind of like test to show, well, this input should map to that output, and then this is the program that actually does the transformation. Other than that, this is not something that occurs that often, right? As compared to, for example, comments and other like things explaining code. So because there's like a modality shift and because this is not something that's very common in the training data, the models aren't as good at it. In cases where especially the inputs aren't very common, right? Like it will work well for English names or for, things that are very common. But if you then change it to like, random character strings, like someone is trying to do transformations on like identifiers in a spreadsheet or some other kind of like very strange data that's very unexpected for the model, the tokenization will break and it will make very subtle mistakes. And that's an issue that the symbolic models just do not have, right? They very quickly give you an exact and provably correct or like not correct sound solution, which I think is like a very, very, very cool aspect.
I think you just spelled out the bull case for, program synthesis, which is like, constrained, amount of data sources, incredibly efficient. These are the kind of, differences against, the large language model, like in terms of just tons of scaling, the input data to train the models. And then, I don't know, just, a lot of, not necessarily correct or even, what was the word you just said? Sound, not necessarily sound, and definitely not verifiable or, it's interesting and not a clear spec, for instance. So, all right, this is so cool. And what about like, you mentioned KU Leuven. What was your path to program synthesis? How did you discover it and what got you down that path of exploring?
Yeah, it was my supervisor, Le Graat, who had a ERC project on automated data wrangling. It was not automated data wrangling. He had an ERC project on automated data science. And one of the pillars of automated data science is, of course, automated data wrangling. So I was assigned to that pillar, the data wrangling pillar. Where the task specification was like, given any kind of like input table, imagine someone opens a random spreadsheet and they have a table in there and they want to apply a machine learning algorithm to it, right? Would it automatically work? Probably not, right? Like there's gonna be some, like the table is maybe not in the correct shape. Like maybe you have to like fold it or unfold it, or like pivoting or unpivoting. And maybe there's like some missing values because, you still need to do a forward fill because, it's not very pleasant to look at repeated values, right? Or anything can happen, right? There's like very unlikely that the table is like a perfectly relational table. And so the premise was, can we kind of like get it to a relational shape? And so instead of directly like how would data scientists do these type of transformations? By exactly learning by writing a piece of code, right? A data scientist would take pandas or like whatever library they want to use or R, and would write a small snippets of code to do these kinds of like transformation, right? So it seemed very obvious that we should try to learn these kind of like programs that then transform a table into a way that's fit for data science. And then knowing that like then the next kind of like problem pops up, which is that typically in program synthesis, you have some kind of like intent, right? In like a lot of synthesis, a lot of the symbolic synthesis, the intent was an example or like a formal specification or something. There's something that says, what do we want the output of this program to look like? And for data wrangling, that was not very clear in the beginning, right? We just knew that it had to satisfy some properties. But then it turns out that if you specify these properties really well and do some kind of smart heuristic search through possible programs, if you find a reasonably simple program that transforms your table into something that, gives a decent heuristic score, it's very likely to be correct, right? Like people are the kind of mistakes or the kind of like imperfections in these data tables, they're not completely random, right? They are going to be very structured. It is going to be something like you need to do a forward fill or a pivot or unpivot or removing empty rows or something. It's like a very, very structured operations. It's very often not going to be this kind of like one-off things. Okay, I'm going to have to change like one small value somewhere, right? And exactly because it's these kind of like common transformations and these common like patterns and the mistakes that the predictive program synthesis approach actually worked quite well. Then once we were able to convert the shape of the table, like very structural transformations, the next part was like feature wrangling. Again, you have a string and like, for example, you have like a paragraph of text from like a house description, or anything kind of go like some kind of location thing, right? And now you want to apply some kind of like machine learning or clustering. The text string is not going to be very, very useful. Again, what would your data scientists do? They would write a piece of Python code or like some other code that would take a column and transform it into usable features. So we could repeat the same idea. Right now, imagine we have a column of strings, right? That's definitely not a good feature. Can we turn that into a good feature? So again, define some function that transforms strings in meaningful ways, like splitting it or finding some kind of like regular expression patterns and extracting numbers and all of these kind of like stuff. And then if you take a proxy heuristic, like either which column you want to predict, which is like very reasonable to assume, you can essentially just wrangle a bunch of features, like you generate thousands of different features and then use some kind of feature selection method to see which of the wrangle transformations are good. And then you can just prune everything else. And you can repeat it for a few steps. It actually works quite well, given that your feature selector is quite good, right? So it's again predictive synthesis, because the intent is like, you're assuming that the intent is classifying something, for example, but then this gives you a very good heuristic, right? You use predictive power of using that feature as a heuristic to see, is the program that I'm writing extracting a good feature? And that were like the kind of like fun things that I started with. And then
fascinating.
Most of the inspiration for this, right? Because look, he knew Summit, or at least they had met at Dashtool and maybe some other places. And so the flash fill algorithm was actually a large part of like the inspiration for Luc to go into this direction and to explore data wrangling program synthesis as part of this automated data science project. And one day he just came into my office, right? And he's like, "Chris, this like flash fill thing, I wonder if we can teach something about the world, right? Like it's not very good at dates. Ooh. I wonder if we can teach it something about like dates or other things, right?" And that got me thinking, because that that got me very excited, right? I was like, ooh, this sounds like a cool idea. And so the first version that we did was if someone needs to know something, where do you go to find knowledge? You go to Wikipedia, right? That has like a tons of knowledge, right? LLMs didn't exist yet. We couldn't go to LLMs yet, right? So you'd go to Wikipedia. And luckily for us, there's a very structured version of Wikipedia called Wikidata, which essentially extracts structured triplets from Wikipedia. So it's like a very large knowledge graph that contains things like, okay, the capital of Belgium is Brussels, right? Or some things like some kind of information like this.
Which is where you live, by the way, right? That's where you're calling from.
Belgium, yes,
Yep.
I'm from Belgium.
Cool.
Good way to segue this into the story.
No.
And these kind of like triples, that's a very like nice way, right? Because they're also annotated with like types, and the edges all have a name, right? So you'd have like one node would be Belgium, and then you'd have an edge capital, and then you end up in another node Brussels. And so then I had the idea of like, can we use this to kind of teach Flashfill about the world, right? So if you have imagine you have a column of like country names, and then right next to it is a column of numbers, and you want to, in your third column, you want to create a column which has this currency symbol of the country, and then the number attached to it, right? It's a very synthetic example, but it works well for this use case. Now, this is information that you would find very easily on Wikidata. If you could link each of your country, the country column, to different country nodes in the Wikidata graph. Then if you take an edge with the same name, in this case, the currency edge, you end up in all of the nodes that represent the currencies of those countries. And those nodes in turn have another edge, outgoing edge, which is the symbol, which ends up in a string value that is the symbol of this currency, right? And now, if you essentially take these two hops, you end up with essentially a new column that you can just add to your table as is, right? So you could take your original table, you have your country, you follow a few nodes to this graph with the same edge, and each consistent path that you follow will give you a new column that you can add to your table. So I could add like the names of the currencies, I could add the symbol of the currencies. You can add a lot of like properties about countries to your table. The cool thing is that you have an output example. So you know at least one of the characters from this property has to be either the euro symbol or one of the numbers that you want to attach it to, right? So you can very easily prune the set of properties that you want to use in this algorithm, that you want to add as like a hidden column to your input. And this worked like surprisingly well, right? I mean, admittedly, some of the examples were kind of like synthetic, and the symbolic part had to exactly match what was provided on Wikidata. Sometimes experiments would just fail because someone had changed a string value on the Wikidata, so something completely different, because of course it's like a collaborative effort. But the idea worked surprisingly well, and it was really, really fast, right? If I use like a cached graph of Wikidata, it would take milliseconds to do these kind of like semantic transformations, right? And there's a lot of information on there. And that was very cool. And then as I was talking about this with Sumit, right? So I had reached out to Sumit like before. It was actually Sumit who suggested the idea of adding this as hidden columns. Before that, I had reached out to him to ask Sumit, is there a version of Flashfill publicly available so that I can try to integrate this knowledge graph approach into the Flashfill learning algorithm directly? And then it was Sumit who suggested, no, there is not, but you can just add it as columns to the input, right? So that was his idea. And then the first time that I actually had a call with Sumit, right? I gave my whole presentation about this like knowledge graph idea, which I had like extended and formalized like very nicely, because you could also learn qualifiers on these properties. For example, most countries have had multiple currencies at some point in time. So of course, you would essentially, it wouldn't be a function anymore, because you would go from Belgium, for example, to euro and Belgian franc and like what other currencies are have. So how do we know which value to put in our column? But we could very easily learn a constraint on a qualifier. For example, each of these currencies are like a start date and an end date. And we could just take the currency that does not have an end date, right? So we learn a tiny constraint on the path that we have to follow to end up with a function again, which maps every country to exactly one property that matches, right? So, and because we have the output signal, we can very easily learn this, right? So that was like, I explained it to it and he was like, Gust, that's nice and all, but we now have this thing called GPT-3. It's like a large language model and it knows a lot of this kind of information. So can you find a way to integrate GPT-3 with FlashFill, right? And that's
beautiful.
I mean, for me, that was an absolutely golden opportunity, right?
Yes.
Just as, you are right now. At that time, I was a very big fan of Summit and FlashFill and the PROSE team. And that was my first chance to actually collaborate with him. So that was like a really...
that's before you joined the team proper?
Yes,
just
that was before
PhD.
Yes, that is just during my PhD. That was like,
okay.
It was like a golden opportunity that I was given the opportunity to...
You were meant for this team. I mean, you were already working on spreadsheets and, adding features to FlashFill, like before you even joined, like very obvious that they would want you to join.
Yeah. So, I mean, and this was a very good chance to prove myself, right? This was like this, if I could do a good job at doing this integration of FlashFill with GPT-3 and with the LM side, that would be the best, resume I could ever send them, right? The best resume is just showing that I could do good work. And that's really when the fun started. That's when like the real collaboration with Sumit and also Vu started. And I really had a blast during the collaboration. It was very, I was very excited to finally I didn't get a copy of the FlashFill code. I had to re-implement it based on top of the framework that they gave me. So that was the first challenge. So it was a very minimal version, of course, not as good as the production version. But that was like a very, very, very cool opportunity. And that's exactly how we ended up at the paper that you want to discuss, or like that I want to discuss actually today.
Me too. That is so amazing. What a cool story. I mean, it's a very instructive story for people who are looking for a job somewhere. That's, like if you know where you want to go, don't wait for permission. Just start working on it. Show your work to that team. That will make you stand out just way more than other candidates who are just applying to hundreds of places and don't have any real, passion about that particular company. I mean, can you imagine like Gus coming at you and, being like, here's all these features, like, let's work on a paper before I even join. Like, I mean, that is just really impressive. And it worked out. Okay, before we dive into this paper though, maybe we could cover just a couple of terms just so that people have some familiarity with things. I think in your examples earlier, you mentioned this, but this kind of programming by example, this is something that comes up in program synthesis. Can you just explain what that is and give like a real concrete example of programming by example?
Yeah. So in programming by example, the specification, which means the thing that you want your program to do, is fully defined by input-output example pairs. So the input can, for example, be Gust Verbruggen, and the output can be GV, where you take the first letter of the first name and the first letter of the last name and concatenate them, right? Everything that you need to know to solve this problem is contained into these examples with some heuristics, of course. And that's exactly what programming by example is. Given an input example of what your function to take as input, given the expected output of what you want your function to return on that input, the goal is to find the function that actually does this kind of like transformation. Typically, more than one example will be given, input-output example pair will be given, because from a single example, the problem is not very well defined. The example that I gave wasn't very good, but if my name both started and ended with a G, how would we know which G to take, right? We'd need to kind of like either take a guess or have like a very good heuristic on this one. So the more examples you then give, the more you can constrain your actual specification to have like one very concretely defined problem statement.
Here's another one that I think is interesting. Definitely as someone new to the field, like I would struggle with is like, you talk a lot in the paper about syntactic, but that's, different than semantic. Like, can you just explain like what do those two things mean and what's the difference?
Yes. So in syntactic means that all of the information to solve this problem is contained in the combination of your input-output example and the programming language, or like the domain-specific language, what we typically call, which is essentially just a few functions that you implement in a programming language. So all of the required information is contained in this combination of your input-output examples and the programming language that you're using to solve this problem. For example, in the GV example that I gave, all of the information is there, right? It is in the, taking the first character of something in the concatenation operator, and then in the input-output example. There's no external knowledge source that's required for somewhere. Now, if you go back a little bit to the previous example that I had, where you were mapping a country to the symbol of its currency, that requires external knowledge, right? There's no built-in function in Python that returns the currency or the currency symbol of a country. The examples don't say for new inputs, what's this currency going to be? So you're going to need some kind of like external or semantic knowledge to know exactly what the goal is. Other easy examples are, that's not like a very good example, but something that like typically considered a semantic example is like transforming like month numbers to their month names, for example. Of course, there is a function in Python, but in most like naive string transformation languages, there will maybe not be a transformation like this, right? So it's everything that you need some external information for is what we would call semantic.
Crystal clear. I love that. I'm so glad I asked because I actually learned a lot there. Thank you. I think you kind of set up, the sort of starting point of the paper, which was introducing LLMs to this kind of, flash fill, program synthesis world. So the premise makes sense, and that is, considered neurosymbolic, I guess, because you've got the neural network and then the symbolic side. So that's the hot topic is this idea of, neurosymbolic kind of looking more like the way the human brain works than, say, just LLMs by themselves. But there's sort of an implicit problem you were kind of stating with that thesis at all, which is like there's some issue with program synthesis. Like it falls short somewhere that we would need these other tools to help with. What is that precisely? Where do you think program synthesis is kind of not enough?
There's two limitations about this, like semantics or incorporating semantics in program synthesis that we face, right? One is just the expressivity of the domain-specific language, right? So, which is the things like transforming a country to a currency symbol, right? A lot of like the languages are just like not expressive enough. And this is where we would ideally have some kind of like neural knowledge base that can do this kind of like transformation also under like slightly noisy inputs, right? So, for example, it doesn't matter if your country is like lowercase or uppercase, or you have like a shorthand version of it, right? If you would work completely symbolically, you would need to store every single combination or, of like how people refer to a country. Whereas, the neural network counts as some kind of, hidden big database that stores all of this kind of like data that we can use to increase the expressivity of our language. A second problem that can sometimes come up is the learning problem itself, which is imagine the language is expressive enough, but it just does not have the input-output examples themselves are maybe not exactly clear on what is meant, right? And there a neural network can kind of like capture the common good, right? For example, if you have like a name that starts and ends with a G and you want to map it to GV, any neural network will make it very, will think it's going to be the first letter because it doesn't make sense to take the last letter of someone's name and then the first letter, right? The concept of initials is like a thing. And like a classic symbolic synthesizer will not know this kind of thing, right? It won't know that these are names, and it won't know that in names, taking the first letter is more common, right? So this is kind of like the semantic limitation of a like symbolic learner, where the DSL, like the language, is expressive enough, right? We can easily write a function that does this transformation without a neural network, but it's very hard to know which program like is needed exactly without really understanding the domain and the inputs that this language or this program has to act upon.
Totally makes sense. Okay. And then the kind of flip side of this is, and I think you mentioned, one aspect, which is like efficiency and cost. Language models, they have, ever increasing impressive, few shot capabilities. Why don't those get us all the way there? Why don't we just switch to LLMs? Flash fill becomes all LLM based, and and I think you've kind of hinted at some of that. But are there some places specifically where LLMs kind of fall short?
It's kind of like hard to say because everything that I say that someone training an LLM then hears they'll use, and the next version will be able to do it. So
cramming knowledge into the models.
Yeah, exactly. I remember like initially some of the like very popular things were, what were the examples that Sumit would always use? Like we would know that it was like bad at counting, right? So for example, if you would take like, as input a character and then like a number, and then the output would be that character repeated that number kind of times. That would work for very small numbers, but it would very quickly break if the number got too large because the model is like very bad at counting, right? So that's kind of like one domain where we used to fail. And of course, as the models get bigger, it's going to get slightly better at these kind of problems. As the models get bigger, they'll automatically write like, programs that do it kind of easily. So that's one. Second is the thing I hinted at earlier, is the kind of like perplexity of the input output. So the LM will look at your text as tokens. And if your input is something that doesn't look like normal text, the tokenizer might do weird things, right? And it might kind of see a string of tokens that it definitely does not recognize. Imagine something like, take like a hash of something, or like a base 64 encoding of something, right? If you take these kind of like characters, it almost looks kind of like random. And in these cases, the model will not do a very good job, right? I think there was like a paper called like the Sparks of AGI or something. Mm-hmm. It was called.
Yeah. Great
so
title.
There, I love I love the examples where they would take a problem like ROT13, where you would take as input a word, and then the output is that word, but every letter is replaced with the 13th, like the letter in the alphabet that comes 13 positions after it, right? That's like a very common encryption scheme. Why 13? Because if you write your alphabet in 2 columns, you just have like essentially an encoder-decoder table that you can use to very visually encrypt and decrypt the message in this way, right? Now take ROT12, or instead of 13, you take the 12 hops, right? It's to a symbolic synthesizer, this would basically be the same complexity because it has no idea that this 13 is kind of like a different thing, right? So very, very simple problem. But the models very much struggled at these kind of problems, and the drop-off was like, I'm not going to name any numbers because I don't remember them, but it's like an extremely significant drop-off going from like a very common problem, like a very common instantiation of a problem, to something that was like more uncommon. And of course, as soon as you notice, you can kind of like instill all of this information in your training data, and the model will become better at it because the tokenizer will be better, and the embeddings will be a bit smoother and everything. But in general, there always will remain some kind of like limitations in the space, right? Even not looking at the cost, for example, or there's 2 aspects to cost, right? There's the aspect of just the raw cost of like doing all of the inference. There's also the cost of like repeating inference, right? Where if you learn a program once, it's like very easy to just like repeat it a few times. I need to just like run that program. Because now I realized that I was like already mixing 2 things, where there's actually 2 things that LLMs can do to solve programming by example, right? There's, I think it's like a program transducer and a program inducer, where I think in one of them, the model is acting like it is the program itself. So if you gave it like, like the model would not write the code that solves the problem. It would really just give you the outputs directly, basically, right? Mm-hmm. So instead of like the model saying, take the first letter and take the second letter and then concatenate them, it would just give you, for any new name, it would give you like the correct, the initials, right? And then the program, like the programming by example, is to really learn some code to actually solve the problem. But the limitations kind of stay the same in both. It's better at the program transduction, so it's better at directly predicting the output, because the patterns are like just like significantly more clear. But a lot of the like counting and tokenization issues, they remain an issue for both of them.
Yeah, and I was just going to say that, like, we're pretty zoomed in on the examples and in the specifics here, but like if you zoom out, if you have to, retrain on specific cases to be able to get the outputs you want, you will never have AI capable of invention on its own, right? It will be, generalized past distribution, but it won't necessarily do like what humans do when they can kind of create net new things, and I think that's kind of pointing out that limitation with LLM only kind of, arguments about getting toward, for instance, AGI, like artificial general intelligence. Okay, this is great stuff, Gus. Like I'm really enjoying this. Thank you so much. It's like a master class in program synthesis already.
Happy to be here.
So I guess the next thing to introduce maybe that's a big part of the paper are these semantic operators. So you've explained, what makes a sort of semantic component of all this. Should we introduce them? I guess, why did you pick 3 to kind of work on in the paper? And yeah, do you think what do you think? Should we dive into each one and just tell people what they are?
I think maybe we can start with very, very roughly explaining how the flash fill algorithm works, because the decision of how we came up with those operators is very much ingrained into the way the flash fill algorithm works. So given the first thing that is, it defines a very simple domain specific language, like a DSL of programs that you can generate, right? It typically starts with a guard that says like, if some condition is true, use this program. If some other condition is true, use this other program. If some other condition is true, use that other program. And most of those programs are then a concatenation of some other things that can be extracted, right? So you start by defining like the space of possible programs that you can describe. Then what the synthesizer will do is the second thing that you define is for each of those operators, you then define a witness function, which essentially tries to capture as well as possible, given that I know what the output of something is, what could the inputs have been. For example, take the string GV from before, and the input was like, look, it doesn't even need to know the inputs, right? Imagine you take the string GV and the concatenation operator. What are all the possible things that you can concatenate to each other to get the string? It's the empty string and GV. It's a G and a V, and then GV and the empty string. So there's 3 kind of like different options of how you can get there. Of course, concatenating something to the empty string is often like quite boring. So here the witness function can like trade off some like completeness for slightly more efficiency, because there's now 3 less options that we need to consider here, right? So we've taken our string, we have defined our witness function, and this essentially allows us to recursively break down the final output into these kind of like smaller pieces that we then need to find in the input somewhere. If the output that we want is GV, and we know that one way of obtaining this is concatenating a G and a V, the problem actually turns from find GV to find a G and find a V. And then, okay, how do we find a G? Again, we go to now we can actually like look at the inputs, right? And now we try to figure out like, okay, if I see any word in my input, okay, there's a column and the first letter is a G, then actually the witness function for this operator would be like, okay, given that I have I need to find a G, and what are all of the arguments? Like, I think this is like a conditional witness function conditioned on the input. So given that the output has to be a G, and given that the input is, Gust, what are all of the number of letters arguments that will make this work? And in this case, it's like a 1, right? And so basically, recursively, you're breaking down this like big problem, like find me the total output, into all of these kind of like small subproblems until you encounter a subproblem that you can solve using an operator from your DSL, that you know how you can solve it using your DSL, right? And that's a very cool thing, because for one, it allows you to kind of like build the space of all possible programs that can transform your input into your output, right? Because the witness function doesn't just return one way of building the output, it will consider all of these. And for each option, you then have like a new subproblem to solve, right? And so that's like a very, very, like, in my opinion, it's still like this kind of like, I think Sumit called it deductive backpropagation. It's still one of my favorite algorithms of all times, just because I like how efficient it is, how widely applicable it is to like a bunch of like problems, as shown by the Flash meta framework and all of these different instantiations of this same algorithm. And of course, here is where the semantic problem comes into account, right? Because now you've taken this algorithm and you've taken the example of these, the input is a country and a column of numbers, and you want to find the symbol of this currency. Now, if you would break this down into like small pieces, you would break it down to like, okay, your currency symbol and then your number, or the currency symbol and the number and then the other number, blah, 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 right? So you find all different ways of piecing together this final output. Of course, in this case, there's always going to be, you're not going to be able to solve any of the there's always going to be a final subproblem that you can never solve. For example, we don't know how to find the currency symbol, right? There's like no way. I mean, we will know it for one row, because for one row, you can just assume it's a constant, right? Like maybe in every row, it just wants to find euro, but then look at the second row and you find like a dollar sign, and it's not going to be a constant, right? So there's always going to be some subproblem that cannot be solved. And so to flash fill, the problem will then think like it will be seen as unsolvable, right? And that's what we wanted to fix, because now the idea was that, like, can we define a operator that is powered by the large language model that would allow us to solve this specific subproblem, right? That would allow us to map the country and the number to, for example, for Belgium, the euro symbol, for the US, the dollar symbol, right? Like, is there any kind of like function that we can write? And that's actually fairly straightforward, because we have an example, right? We know what the output is. The output is the currency symbol. And we also know what the inputs are, right? So it is the country and then the number, because we don't know yet that we don't know that it's not the number that we need, right? Now, as you mentioned before, the model becomes very good at in-context learning. So it becomes good at this kind of like few-shot learning. You give it, the input is, this country and the number, and the output is a euro symbol. Now, if you take a new row, you can just give it the inputs for that new row and then an output, right? I think in the paper, I just use like a very simple arrow-based format, right? The input is literally, Belgium, 10, arrow sign, euro. And then the next line, it would be like US, 20, arrow sign. And then the model would just complete, we would ask for the model to complete it, and it would complete it with like the dollar sign. And that's essentially is our function, right? The language model, every function invocation is just a prompt that we route through our language model that then uses the in-context few-shot learning to get us our output.
Okay, got it.
Now, this is the map operator. That's the one that we mainly implemented. We could do the same thing with kind of like a guard, right? We could easily ask a prompt that kind of like defines, is this thing true, right? Or like, should we use this or this program, right? Like essentially the input is the input and the output is just like a Boolean value. So it's kind of like very, very similar. And so we have this, and then we also have like the semantic position operator, which would again be very similar, right? So imagine you have the problem of taking a sentence and you want to mask the first verb that you encounter, right? So that requires a lot of like semantic information, because you don't know what a verb is, right? So the syntactic still like will never know it. So the program that we would get is like, okay, you would take the string up until some position. Then we would take, a bunch of like underscores, and then we would again take, the strings starting after some position to the end, right? So we need to find what's the character position right before the first verb, and what's the character position right after the first verb, right? And again, Flashfill already had like a position operator, right? So the thing I discussed earlier, where, this concatenation would then find the first character, the one would actually be an absolute position operator, right? So it keep going. It would keep going back like this. So now at some point, we know how we can build the output. We know that one potential way of building this is, okay, we're going to have like the input up until the first verb. We're going to, like every day we know what the position is. Then we're going to have like, we know what the second position is, right? And now we essentially need to ask a language model. I mean, given that I need to find this position, like what could that mean, right? again, we are given an example. So we could say, for example, like, okay, this sentence has to be mapped to 13 and this sentence has to be mapped to, 18, right? So that's something that we can know from our deductive backpropagation. Then the model will very easily see what new position as we would need to find. So if we then give it a new sentence and ask it what number do we need, it will be very able to see, okay, I need 30. Of course, this is not exactly how it's done because, as we mentioned before, the model isn't very good at counting. So now, instead of implementing the position as like a counting prompt, we implemented it as a substring prompt. So the model was asked to output the string that we need to find in this sentence to then find and then we would just take the first or the last position of that string that we find. So the model, the actual position operator would be implemented as, okay, the input would be, the string, the output would be the verb. And then the model for a new string would output the other verb again. And then this verb, instead of using the verb directly, we just take the first and the last position of it. There's some clear limitations, like, if there's like repeated strings or something like this. So we kind of like abstract it around all of that. Because, there's probably a way around it, but this is how we get to kind of like the semantic operator, right? Like the semantic matching for like the Boolean guard conditions at the root of the DSL. Then the semantic mapping operations for if we want to essentially do a lookup in its knowledge. And then the semantic position for if we need to know, take substrings that depend on semantic conditions.
Perfect. Okay. Totally makes sense. Are there tasks that kind of still remain out of scope? I mean, it's not like an exhaustive list of semantic operators, right?
Technically, any task that the model can solve through program transduction is now in scope. Because one funny thing is that technically any output string can be considered as an output from the model, right? So in this kind of like witness function for these kind of functions, we're always assuming that the model will be able to find a solution, right? So for these other witness functions, we know that that's not the case. We always know that obviously the concatenation is not going to be able to solve any problem at any point in time, right? But so for this language model, we kind of have to make the assumption that these semantic operators will be able to solve all of the problems thrown at them, meaning that if you take your semantic map and you engrain it at the level of something that can be concatenated. So your concatenation can take like a string that you find from somewhere. One of the ways of finding this string is the semantic map operator, right? That means that everything that's output by the witness function will go through the semantic map function. So basically, imagine like the output is, so the example we had with like the sentence that had like a verb in it, right? Like maybe it's like, I love pizza, right?
Okay.
So how do we build the string I love pizza? It can be a concatenation of a lot of stuff, right? It can be I and then love pizza. It can be I space love pizza. It can be I space L of pizza. So there's like a lot of different ways. All of them will route through the semantic map operator, right? And it will for all of them say, yeah, I can do this. Yeah, I can do this. Sure, I can do this. And of course, one of the ways of finding the string is just, concatenating the empty string to something. So then basically the whole output can also be generated by the LN, which is a very nice property of the algorithm, right? Like if the whole problem is semantic, it will still be able to solve it. But as soon as a small subproblem can be solved symbolically, that's what we favor, right? So we technically learn all possible programs, right? That's like one aspect of FlashTel I mentioned before. It will not learn one program. It will learn all possible programs. It will then rank them. And we simply rank the programs learned by having the fewest characters produced by semantic operators possible, right? Essentially, what's the cheapest program that we can now learn that will get us our solution? And that's the top one that we return. So even if a problem is completely symbolically solvable, right, it will never use a semantic operator because they're very heavily punished for using it, right?
It's like MDL.
Yeah, exactly. Yes. So we're trying to kind of like rank it by like what's the cheapest way to build this output. And the LM functions are very, very expensive.
This makes so much sense. And by the way, I think you just kind of dropped the key insight of the whole paper, which was decomposing tasks into like subproblems and then, delegating only the like semantic stuff to the LLM and vice versa, the sort of like how would you say it? Can you put it in your words, like what you think this sort of key insight is that you just shared?
I think the key insight is exactly this, right? Like, we shouldn't use the language model as kind of like a black box that needs to solve everything, right? There's a lot of like parts of these problems that we can solve symbolically, right? And so this is a very, it's essentially just taking that to the extreme, right? Like finding the smallest possible subproblem that we need a language model for, to solve, to make other problems solvable. In a way, it's kind of the inverse as tool use in LLMs, right? Like nowadays we know that LLMs, like they're bad at counting, but the model can very easily, if you give it access to a calculator tool, it will then use the symbolic tool to figure out what, 1 plus 2 is, right? And this is exactly the same. So there, the main orchestrator is your language model solving like a big complicated problem, and it has like a small symbolic tool that it can use. And in this paper that we did, that existed from before the tool use, was exactly the opposite, right? You have like a big symbolic orchestrator, and you would use the LLM somewhere in the leaf where it needs to solve a subproblem that we know the symbolic part isn't very good at.
This is so cool. It's reminding me of, in the software world, this kind of concept of determinism versus non-determinism. And, do you flip your whole software to be non-deterministic now that LLMs like run everything, and then, use tool calling for like the more symbolic stuff to things that could be the precise syntactical structure, I guess. Is that syntactical even a word? Syntactic. There you go.
I'm not a native English speaker. For me, syntactical is a perfectly valid word.
All right, let's go.
I've probably used it in a paper somewhere.
Hey, all right, I love it. It's official. You heard it here. Gust has approved my made-up word. All right, so other pieces of the paper that we haven't talked about yet is this kind of what is this deferred query execution? I'm not sure I fully understood this part. So can you break that down for us? What's going on there?
Yes, that's actually a solution to a technical property of the flash fill implementation, which is after a witness function determines these are possible inputs that you can use to build this output, what it will do is it will actually try it, right? It will say, are you sure about this? I'm going to actually try piecing together, concatenating these strings and seeing the output is what you say it is going to be, right? So it's called like a soundness check, where we make sure that the program is actually sound. Of course, if we use a semantic operator and we want to do some kind of like soundness check like this, that becomes like very, very expensive, right? We don't want to actually run all of these, possible LM queries. So it's something that we then only do at the end, right? Exactly the part where we let the LLM always say, yes, I can do this. That's exactly the deferred query execution, right? Because we're just assuming that it can do it. And then so the synthesizer is able to build the space of all possible programs with these kind of like the like deferred like LM operators that haven't been tested whether they can actually do it, right? But we're kind of assuming, right? We're deferring this decision until after the ranking has been made. And typically, because we end up with the smallest possible subproblem for the LM, it will be able to do it. And now, if you give this model any problem, it will always give you a program. Like it will always tell, yeah, I can do this, right? One thing that we could actually do is now, as soon as you have more than one example, you can just try to use one of the examples to predict the other, and vice versa, to know, can the model actually solve the subproblem, right? And then this is the thing. So we would have to do the soundness check on like some of the given examples, at least if, like 1 or 2 times, to kind of like eliminate further possibilities. And that's not something that we did because we didn't really go ahead and implement it anywhere in production. But that's something that we probably want to do before surfacing this to a user, right? Because that gives like a very, very, very loose, soundness, at least heuristic on will we be able to solve any new problem that the user is giving us.
The paper mentioned something you called it greedy clustering. I'm guessing this is like grouping of the results that we were talking about, the ranking earlier, where you penalize the language model, functions. Is that right? Like, what is the greedy clustering?
Clustering is actually for when you want to have a semantic map operator, right? But you have multiple examples. So in the semantic map operator, it will combine all of the, like, there's actually different possibilities for imagine you have, for example, you want to map Japan to the yen symbol, right? Or the yen symbol and a space, and the yen symbol and a space and a 10, right? Because these are all different kind of like different specifications obtained through your concatenation operator, right? If your output is a yen symbol, a space, and a 10, then we can get the yen symbol, we can get the yen symbol and a space, we can get the yen space symbol and a space and a 10, right? Then for another row, we maybe have like France and 20, and so we'll get like the euro symbol and a space, and the euro symbol, a space, and a 20, right? All of these are possible ways of finding the output for two different rows, right? Now, you can already see that this technically gives us a lot of different ways to kind of like build this row, right? So we need to like essentially take the cross product of these to figure out which one can be learned. And the semantic map operator will just say, I can do all of them, right? And how the semantic map operator works, actually, maybe this is something that we need to talk about, right? Like an interesting sidetrack here, is that typically in Flashfill, it will learn one program for each row, right? It will learn one program space for each row. So all possible programs that are true for the first row, all possible programs are true for the second row. And then it will take the intersection. So it will take all programs that are true for both the first row and the second row, right? So it will like shrink the number of possible programs by making the specification more specific. Now, the semantic operators, they grow when we add more rows together, because now they are giving us more signal, right? If we have one row, right? Like if we would learn a semantic map operator for one row, we would, for example, learn that we can map, Belgium and 10 to a euro symbol, and US and dollar to a US and 20 to a dollar symbol, right?
Yeah.
Now, what we do then is we essentially combine both of these examples to build one prompt for the language model. So the semantic map operator kind of like condenses all of these possibilities together, right? And now, because at this point we are building, like we are going to get like some exponential complexity, because for every row, the semantic map operator will always say, yeah, I can do this. Yes, I can do this. Yes, I can do this. Right. And so essentially it will get like a very big blow up and the kind of like questions that we can ask the language model. So we can map, for example, in the first example, we can map, Belgian, to, the euro symbol. And in the second one, we can like map, US to the dollar symbol and a space, for example, right? This is one possible combination that the semantic map operator will kind of like get. And so what we do in the clustering is we reduce this set of possibilities by looking at like syntactic patterns inside of them, right? So we will essentially, if you take your concatenation operator and the first argument to your concatenation is going to be your semantic map, right? So for example, we need to find the euro sign and a space, and then the euro sign and a space and a number that comes after it, right? That's for like the first row. For the second row, again, we have concat. On the left, we have the semantic map again. The semantic map then again has the different options, which is mapping, the US and some number to the dollar sign and a space, and then the dollar sign, the space, and the number. That means that in that semantic map operator, there's already, because the first one is 3 times the second 3, there's going to be 9 different options. Of queries that we can ask to the language model, right? So we're essentially going to generate in this kind of like tree in the deductive backpropagation, we're going to instantiate 9 different nodes, right? And so we know that that's too many. And we also know, because each of these that can then again go down for each node on the left-hand side of the concat, we're also getting, of course, a node on the right-hand side of the concat, right? So blowing up one side of a concatenation with semantic map operators will automatically blow up the rest of the search space, because then the other side of the rest of what has to be concatenated will also kind of like blow up. And imagine that happening this recursively at every step, right? So then search space becomes like very, very massive. So one
Yeah.
thing that we do is we want to kind of like reduce this 9 to as smallest as possible, right? So we know that ideally in the first one, we have like 3 different options. So we instantiate 3 different clusters because we know that for each of these, one option for the second row is going to be the most closely related to this, right? For example, if we pick in the first one that we just want to have the currency symbol, then we know that in the second one, we're very unlikely going to need the currency symbol and the space, or the currency symbol and a space and a number. So if we do syntactic clustering, we can like essentially, we take the first one, we know there are going to be at most 3 possibilities. Then from the second row, we just assign each option to the most likely one. And then for the third row, we again assign each option to the most likely one. And so this is like a very, very kind of like greedy clustering approach where now the left-hand side will only have 3 different options instead of 9, right? And that's for a very short string. So for longer strings, we can like even more drastically shrink the search space by, greedily clustering the different options that we can get in this semantic map operator.
That is so cool. Thank you for taking us through that. This makes sense. That's very clever. So we've got our semantic operators. We've got this kind of greedy clustering. We've got the ranking you mentioned earlier. What are the results? Like what happened in the end? Just curious what your thoughts are on that. I know it was a while ago, but do you remember?
There's no sense in comparing it with like a regular flash fill. One thing that we did is we compared normal flash fill, like symbolic flash fill problems, and we threw them at, back then it was GPT-3. And of course, most of these problems will now be solved, but similar, more difficult problems are still not solved yet. And there we could very clearly see that one, there's a lot of problems that's unsolvable by GPT-3. For example, because, the strings look not what it's seen and it's looked like nothing that it's seen in its training data. So it doesn't know what to do with like tokenization. Or it needs significantly more examples where FlashFill can solve most problems for like 1 or 2 examples. And GPT-3 needs like 7 or 8 examples to kind of really learn the patterns that exist in some kind of like input-output pattern, right? So that's like a core idea. Essentially, first things first, make sure that we can show that the syntactic part is still relevant, right? Okay, that's definitely still relevant. And then the second one, we essentially, because we can also ask GPT-3 model to just output give us the output directly, right? This was like the program transduction I was talking about. There's no program being learned by GPT-3 because the standard programs that it's learning suffer from, this expressivity, the semantic expressivity program that we need for these kind of like problems. So we just asked the GPT-3 model to just like output the final answer directly, right? Which is going to be very expensive, of course. But also we see that it's often like the quality is like significantly worse. Because it's still making some mistakes in kind of like tokenization. So it gets the semantic part correct, but it's typically making some like small mistake in the syntactic part, right? Or it's like it over fixes some stuff. Imagine if there's a name that's spelled with like a small letter, for example, then the model will sometimes just output it with like a capital letter, because that's typically how it sees names, right? So it will change parts of your input-output specification that you did not want it to change. And that causes like the final solution to be wrong, right? So that was like the core result, is that the number of examples is like significantly smaller for FlashGPT, because the problems that we let it solve are also significantly simpler, right? Either it has to go from like just a country to the symbol of its currency. It's like a very simple thing. Or it has to go from like the symbol of the currency and then at the space and the number. And I mean, that's of course a very trivial example, but it gets harder for like verbs and stuff, right? If I need to find a verb and then replace it with something, right? Especially if we replace it with like a number of characters that's exactly the same as the number of letters in the word or something like this. So these are the types of things that are kind of like hard for LLMs to do, that are very easy to kind of like do symbolically.
Makes sense.
Then we, of course, try to do it like with and without clustering, where the clustering like make the average speed go down for like 1 or 2 seconds to like a fraction of a second, just because the search place like drastically decreases. And there's also just like quite a lot of like longer problems where you get a timeout. This is, of course, because my witness function implementations were very naive, right? So if you have like a long string, typically you would find like smart concatenation points, right? Like if you have like a sentence, you know that your concatenation points are going to be like maybe before and after each word and not after every individual character, right? So these are like these kind of like smart kind of like starting and stopping criteria. And here we show that the kind of like number of fake LLM calls that we're making goes down from like, 6,000 or something during a training loop to like maybe 200 by using, for example, the deferred query execution. And in the end, it actually makes 0 of the calls, right? So I think that's some interesting things. We had some other kind of like case studies that I also think were like kind of interesting, like using the model to then rename the semantic operator to something interesting. For example, the previous one is very boring. If you like, imagine a user seeing this program and it sees this like sem mop, that mop is Belgian to a euro symbol. The users are going to be like, what the hell is this, right? I have no idea what this means, right? But then if you could just give this thing to a language model, I feel like name this, right? It's a function that takes one string as input. What would be a function name for this? It could just be like get currency symbol or something, right? So we could actually very easily use the model to rename the semantic map operations to something that the user would actually program, which I think was like a pretty cool thing. Then we have semantic string profiling, which is essentially learning semantic regular expressions. So you want to learn some regular expression on phone names, right? And there's like a color in there somewhere. You can actually learn that, okay, I have like, the first thing is like the brand, like iPhone. Then you have like the version number, like 11. And then you have like a dash, and then you have like maybe a color, like red or something, right? I don't know what the phone colors are, right? Like that's like a very classical example.
Cosmic orange. No, I'm just kidding.
Yeah, some like fancy color name. And then here, what we can actually do is we get learn a semantic pattern that the LM could then also apply to new data to see if it matches a constraint, right? If someone then types in, Samsung S10 computer mouse or something, right? Just naming something that I see in front of me, that's not going to match the semantic pattern because computer mouse is not a color, right? And so this is the string profiling kind of like thing that we also add like something for. And because there exists a string profiling algorithm implemented in Flash Meta, right, which would do a very similar thing, it would again take the problem of turning a string into some kind of like regular expression, breaking down into this kind of like deductive backpropagation. And what you need to find is like, the first token for your regular expression and then the rest of it, and then the second token and then the rest of it, right? So you can kind of like recursively break it down into this problem and then again rank them, and you'll get a pretty good string profile. I think the semantic position, for example, can definitely be used here to, just straight out of the box, right? You don't need to change anything to this to kind of learn problems that do something smart here.
Neat.
That's also like some kind of like case study, right? Where the operators can be very easily used in other algorithms implemented in the FlashFill like framework.
Gus, this is so cool. I guess, okay, here's the last question on the paper, which is, did it get used? I mean, this was all for FlashFill. Sumit was like involved with the writing of the paper and requesting this topic. What happened to it? Like, did it ever get implemented?
Yeah, no. I see. This is. I mean, back at that time, it was still like there was not a lot of like engineering to integrate LLM-based stuff into products, right? So that's like the first limitation. I feel if we would look at it nowadays, that would already be like significantly easier. But there's still like some things like the cost of this can very, very quickly go up, right? Like imagine a user invoking this on a table that has 1,000 rows. You're going to make maybe 1,000 LLM calls, right? So it's basically you need to have one call per row almost. A very beautiful aspect of this approach is that it can enable caching. Imagine like the country to currency thing. As soon as you've learned your mapping from currency to, the symbol, country to the currency symbol, you never need to like look that up again. As soon as you've built this mapping once, you could just like reuse it from your LM cache in some like smart way, right? If you can also get the LM to tell you which column it's looking at. So the input is now like Belgium 10, and then output is like a euro symbol and also column 1, right? And now you know that in the remaining calls, you only need to look at column 1. Your functions, like your prompt changes like a little bit, but the caching becomes like significantly easier, right? So
makes sense.
That's like one thing, but still, right? But still, there's like a potentially significant cost. I think a second problem is that like I still think it would be useful, like it would be cool to integrate something like this, but it's very hard to upfront estimate the potential effect of this, right? So for something like Flashfill, it was a lot of work to implement, right? Sumit did a very great job to kind of build a data set by manually scouring, Excel forums for like questions.
Okay.
Because no one expects these semantic problems to be solvable. No one's going to ask these questions of, can I have a transformation that solves this problem for me, right? Like no one's asking, is there like an automated way of getting this like currency symbol? Maybe for that one, someone has asked it, but for like a lot of the other problems that we came up with, it's not like a typical question that people ask, right? So it becomes very hard to estimate the potential effect. And so it would be a lot of like cost and engineering for something that we don't really know if people would like use or appreciate it, right? So
Got it. Big risk there.
yeah, I think one thing that I think we should try at some point is going back to the knowledge graph version, and using LLMs to filter down these like very big knowledge graphs into small knowledge graphs that are highly relevant to Excel spreadsheets, for example, right? So we could take a big corpus of spreadsheets, we could try to link it through nodes in the knowledge graph, find are there any values or like edges that are, that we also find in the same sheet, and build a very small, high quality knowledge graph that can be used by the symbolic Flashfill system to at least give us some kind of like semantic. So essentially going back to basics could be a very cheap way of integrating, at least the semantic part without the LM.
Very cool. All right. You're kind of hinting at my last question there, but last question for you, Gust. What do you think is like the most exciting thing left to work on in program synthesis, or next to work on? And you were given some ideas specifically for this, approach that you introduced in the paper, but what about just stepping back in general? And it can be something in conjunction with LLMs or, combining deep learning and symbolic AI.
Usually I'm very like application based here, right? Like what's like the cool application? Like you could take any kind of like problem and you can come up with like some research problem of like what's going to be next, like make it better, make it smaller, make it faster, right? So I think there's always going to be like some kind of like trivial thing. So I feel like for the what's next in program synthesis, I think I'd have to think about what is like a domain or like a cool application of something like this.
Yeah.
I'm going to say it's going to be, for me, it would be going back to the code application of the Flashfill algorithm, right? Where we would be transforming ASTs. Now you can view almost anything as a tree kind of like structure, right? Like
yes,
anything can be turned into a JSON document, or anything can be turned into some kind of like JSON representation. Now, if you're able to turn everything that the user is doing into a JSON, like a stream of like JSON representation changes, I think it would be fairly straightforward to learn like repetitive patterns that people are doing on their computer that you are not going to ask some kind of like expensive agent to do for you, right?
Right.
So I'm still seeing a lot of like applications of like essentially taking the algorithm behind this and making it application agnostic, I think would be like a very cool thing for me. Like a computer use agent, by example, that instead of like using like very big neural networks and looking at like visual cues on the screen, would really try to, view your current computer or like a compute environment as a structured document that it can easily write programs over, and then kind of do that. I think that would be like a very cool kind of like application.
Ooh, I love it. This is so cool. Gus, just can't thank you enough for sharing your wisdom on the show. You're so deeply embedded in program synthesis that I feel like you're going to have to come back on, either talk about other papers or somehow we'll have like roundtables and you can become a regular on the show. But and I also want to chat with some of your other teammates too, maybe folks who have done cool program synthesis research on the PROSE team, and Sumit, for example. Like I'd love to have him on. So to be continued on all fronts. But thank you so much for your time on sharing the paper. Really appreciate it.
Yeah, you're very welcome. You're very welcome. I really love talking about it. It's been some time, but it's still like I think, the favorite paper that I've written, and because I think the idea is so elegant, right? Yet it had like so much potential. I can only highly advise to get Sumit on the show. He's a great storyteller. I'd have to apologize to Sumit for already,
No.
spoiling some of the things that he would talk about. But he's like much better than me at telling these stories. And he has a very great video on YouTube, like the story of Flashfill and how it shaped me. Right? It's like a recommended watch for everyone interested in like program synthesis and applying it to the real world.
Yes.
It really has a full story of Flashfill and how it came to be, and how his goal was really just to like help people do actual work. So yeah, I can highly recommend trying to get a hold of him.
All right. I'm going to put that YouTube talk in the show notes so people can go watch that before we get him on the show. But Gus, thank you so much for spending time with us today. And thank you all for watching. We'll see you on the next episode of Abstract Synthesis.